This is a production of Cornell University.
So many decades ago, growing up in the East Hills of Nepal, I was growing all kinds of plants and animals as a child, helping my family. Corn, soybean, potatoes, oranges, chicken, buffaloes, goats. But then we would be doing everything by hand or handheld tools, sometimes using animal-driven tools. But that is the way farming was happening when I was doing farming. That's the first generation of farming. As though we are dealing with or working with individual plants and animals, our decision making is rather anecdotal based on our experiences. If I see corn plants can growing pretty well, taller than others, I would apply just a little bit of nitrogen. Or if a plant next to it is not growing as much, I would apply a little bit more right next to its root zone, and that's the way we'd do farming. And then we saw different computer. We saw advancements in fuels and hydraulics and engines that led to bigger machines and led to the era of mechanization in agriculture, or second generation of farming, where now again we're using big machines to perform various field operations such as plowing, planting, pesticide application, but we are now managing crops and animals at a bigger scale, like plots level, thousands of plants at a time, or hundreds of animals at a time, rather than going into individual plants or animals to manage them based on their needs. And then in the recent decades, we saw a lot of advancements and innovations in sensing technologies, computational technologies, communication technologies, positioning technologies such as GPS or GNSS. Perhaps all of us know what GPS stands for, but GNSS is a more generic term, Global Navigation Satellite Systems. GPS, Global Positioning Systems, being just one example of that kind of satellite navigation and positioning systems. We often kind of assume GPS being the generic one, but quite not. And then that led to making machines a little bit more intelligent, more advanced and automated. We have seen, for example, or many of you, I'm guessing, have seen tractors that can follow predefined trajectories without human intervention. They can go around the field at the end of the row or at the end of the field and come back to the same row or a different row depending on your needs within a couple of centimeters, actually, because when we use real-time kinematic GPS, we can position ourselves within an inch, and that is the kind of accuracy these tractors are using in auto steering. And then in the last decade or so, we have made even further advancements in artificial intelligence, Internet of Things, blockchain technologies, and cloud computing, which have allowed us to be even more strategic and smarter in doing farming, not just field operations, but also in terms of helping farmers to make farming decisions, giving them information around if the plants are doing well, if the animals are doing well, if they're growing the way we expect them to grow, and sometimes even making farming decisions using automated systems rather than having farmers make that decision. So and then bringing that into implementing that decision, such as if I said this plant needs 1 pound of nitrogen, I also have the capability these days, again, there are machines being developed to apply that amount of nitrogen to that individual plant and move on to the next and to the next. So that kind of capability, which brings us to what we generally call agriculture 4.0, or fourth generation of farming, sometimes also called smart farming. So going back, top left, I'm posing some 10 years ago in my village in, again, mid-hills of Nepal. animal-driven agriculture. Earlier, I said that farming was that way when I was growing up many decades ago. Actually, it's still happening the same way. So that brings me to this point that in most of the other industries, such as manufacturing, when we graduate from one generation to the next, it almost happens about the same time throughout the world. When I say that, in the larger schemes of things, it may be lagging by a decade or 15 years, but we're talking about advancement or graduation from first generation farming to second generation some 100 years ago when we developed these bigger machines. But some parts of the world, and in fact, actually many parts of the world, are still in the first generation of farming. That means all these generations, handheld, tool-based, animal-based agriculture to bigger machine-based agriculture, where we are using this really gigantic tractors and combine harvesters and planters, these auto steering technologies I mentioned earlier, some other automated robotic machines for weeding, for example. There have been quite a bit of successes in automating weeding operation. All these generations of farming, they're happening simultaneously around the world. And that's kind of the interesting aspect of agricultural industry. And then when we put all these concepts and technologies together, that leads us to this next generation that we are currently in or are trying to go into, fourth generation of farming, which again incorporates the concept of what we call precision management, management at individual plant level or very small units, so that we can maximize the productivity and quality of that individual plant or animal. We utilize mechanization technologies, but also tools and techniques that would automate those machines and put the artificial intelligence and other decision-making components into this overall mix that leads us to, again, the next generation of farming, where we sense and understand what is happening in plant growth, animal growth, or in their environments, make decisions in terms of what needs to do, implement that decision with robots or automated machines to actually do it, and then also evaluate the outcome of that operation so that we have closed the loop. And that's, again, the fourth generation. Sometimes we call fifth generation of farming. That kind of historical perspective behind, I would like to also talk a little bit about how artificial intelligence and cyber physical systems interact and help us in farming. CPS stands for Cyber Physical System, which is basically nothing but a connected world where sensors, human, machine, plants, animals, soil, all things are connected to each other and talking to each other. And so cyber physical system infrastructure provides us that capability to connect everything that goes within farming. And then to our left is are some of the fundamental algorithms and models artificial intelligence discipline provides us. Those fundamental models and techniques and tools are used to develop various technologies such as pattern recognition, machine vision, big data analytics, decision support robotics. For example, these days we don't even have to touch our computer, it recognizes the patterns of our feet. So if you touch the computers, these all are pattern recognition technologies that utilize some fundamental AI models, right? So these are the technologies. Then these technologies can be used in almost everything that we do in our lives. And agriculture is also not an exception. We do utilize these technologies to perform plant and environment assessment, making farming decisions. I've been repeating these things, but also implement those decisions and analyze the outcomes. Where does it help? But pretty much everything we do in farming, from selecting sites for different kinds of crops, for example, to plowing and planting, and to nutrient and water management, to harvest and post-harvest management. Everything we do in farming has been or can be positively impacted by the artificial intelligence and cyber physical system technologies as they move through these technology development and tool development phases. Now, that kind of conceptual discussion behind, I would like to get into what I work on, which is around automation and robotics for farming, particularly emphasizing what we call specialty crops, mostly fruit crops and vegetable crops in my research. Even then, more specifically, I work with apples and wine grapes, but there have been some efforts in strawberries and onions and potatoes and some other crops as well. Though I consider myself more as a technician who fits everywhere, is crop agnostic. I could be working with anybody, any of you here who might be working in any kinds of crops, and hope to provide some tools and technologies as a technician. Why? Because one, we can do it. I think we have now all the tools to do it. But that's just the secondary part of it. The primary motivator for me, why I want to develop automated robotic machines for farming, is to first fulfill the gap of not having enough people to work in the farms. But as a more importantly, a lot of agricultural operations are dangerous, risky, and pose a lot of worker health and safety issues. As an example, the driver here applying some kinds of chemicals is exposed or has possibility to be exposed to that toxic environment, and it's a lot of health and safety issues. When workers are working in these farms for picking apples, pruning apple trees, thinning flowers, they are working outside 12, 14 hours shift, climbing up and down the ladders in really hot sunny days, like 110 degrees in Washington State, where I was working until like 5 months ago. Really cold winter days when we have to. So these are really laborious, but also harsh conditions. And we would like to create jobs in manufacturing, supervising, monitoring, maintaining automated machines while having these jobs completed by those machines. So that's the philosophy and the motivation behind what I do. There has been long research and development in this area, but only limited commercial success. And a few areas where we're making some progress, such as I mentioned earlier, automated robotic weeding. But then there are a lot of other areas, such as robotic picking of fruit and vegetable crops. We have not been successful so far to commercially adopt those technologies. That's partly because, or mostly because, in my opinion, due to accuracy and robustness, or the lack of desired accuracy and robustness of these machines. There might be a robot that can pick only 60 or 65% of the apples that are there in an apple tree. Among 100 apples attempted to pick, it might be only picking 80% of them. So these are the accuracy issues. In robustness, there might be a robot that works with reed varieties such as Gala and Honeycrisp or Cosmic Crisp from Washington State or Ruby Gold from Cornell. But then if it is Granny Smith or Golden Delicious, it may not be. I mean, just as an example. That's the robustness. Speed. We as human beings are really fast. Workers in these fields are really fast. That's just one aspect. Certainly, eventually it comes down to economics. I'll talk about that too, the next bullet point there. But when we talk about the speed, any guess how fast workers pick apples in commercial orchards? That's a question, not an information.
Apple every 5 seconds.
Human. Any other guesses? Have any of you picked apples?
Yeah.
Many of you picked. This is a wrong audience for me to ask that question. If I'm in engineering, like last week I was in robotics giving the same seminar, then nobody would raise the hands. But still, you perhaps do not have that feel. They pick 2 apples a second. 2 apples a second. Even in the 12-hour shift, whole day, they're picking 1 to 2 apples per second. That includes climbing up and down the ladder, emptying into container bins and everything. They're really fast. Our robots, not quite there yet. My fastest robot is 5 seconds. There are companies arguing that they can pick an apple every second, every 2 seconds, but then they're really big, expensive machine with one hand that moves really fast. Our design has been to have 6 or 12 arms from both sides and pick simultaneously, but they're rather slow compared to human picking. That brings to, certainly speed is issue, brings to complexity and cost aspect. I can make my robot really complex and really fast, but then it becomes really expensive. It's not defense robotics or space robotics, where putting 20 million is nothing. When it comes to agricultural robotics, we are, as we all know, running in really thin margin, sometimes negative margin. And if machines are not affordable, they're not going to make an impact. And that's why cost complexity becomes a huge driver. And my research program and many research programs around the world, we're trying to address these challenges so that we can develop machines that are practically adaptable. There are two primary components in robotics as it applies to agriculture. Navigational robotics are almost like self-driving cars. And manipulative robotics, I can kind of use a phrase, like a phrase I just created, self-doing. Self-driving and self-doing. There is a vehicle that can drive itself around orchards or other agricultural fields or animal farms. And then they also have to be able to do things by themselves, such as picking apples or pollinating flowers or pushing haze, sensing animal temperature, or whatever that is, right? So there have been a lot of progresses in navigational side. It's still a lot of room for improvement, but then manipulative robotics side, we're still in the early stage of advancement. And as I mentioned earlier, we don't have very many successes for commercial adoption yet. Let's talk a little bit more about navigational robotics. Early efforts in 90s and 2000 led to these commercial successes of auto-steer tractors. They are mostly based on GPS or GNSS, Global Navigation Satellite Systems based techniques, some vision-based, some camera-based techniques as well, but mostly current self or auto-steering techniques are based on GPS. But then when you are just using GPS, there is a tractor driving down the field. I know it has the GPS track, so it can keep the tractor within tree rows, apple tree rows, for example, in apple orchards. But if there is somebody in front of it, it will just run over because it doesn't have any vision-based local understanding. Wide adoption, as I mentioned earlier, about 60–70% of the tractors sold around the world, I was told, are equipped with this kind of technology already. Here is an example of early efforts in my lab also to develop a navigational robot that can find its way into orchards and pick apple beans, a container of these harvested fruits. So this was some 10 years ago. It has LiDAR sensor, but it's also mostly guided by GPS. It has some positioning information so that it can go to those beans. This is empty right now. We're testing in the winter, as you can see, but the goal is to have this robot go into the orchards, pick these full beans of apples after they are behind the harvesting crew or harvesting robot at some point in the future, and then bring them outside into the loading areas. Recent efforts in ground autonomy or navigational robotics include kind of both the fusion of GPS and vision systems so that we have larger scale understanding of where we need to go, but then local information from cameras and LiDAR or laser sensors so that we can detect obstacles, we can avoid them. There have been companies working in two kinds of technologies for navigational robotics or self-driving in agricultural fields. One is to retrofit existing machines. Companies such as Savant, Blue White, they're just coming up with kits that you can install into your existing tractor, and that tractor becomes capable of finding its way around. And there are standalone machines such as the machines from John Deere, Goss, Monarch. Monarch is an electric tractor company. They also have a goal to have these machines be completely autonomous and find their own ways in the fields. Successful applications of these navigational robots include smart spraying. There are robots that can find their own ways into the orchards and apply various kinds of chemicals. Weeding robots, such as the machines from Carbon Robotics, have been pretty successful as well. Logistics for agricultural produces, I mentioned about that earlier for apples, where there are smaller robots moving harvested grapes and blueberries and other products out of the agricultural fields into loading areas. So there are some of the success stories, still not broadly applied in farming, but we see some commercial penetration of these technologies into farms, and I only anticipate they will go bigger in the future. In recent years, we also added more capabilities into our own robotic system for apple bin picking. It's called bin hauler. Recently, we sent this robot to a competition, and we're one of the winners, and we were awarded some $10,000, which I left at Washington State, unfortunately. I was thinking about bringing my students to a nice trip somewhere, but then I don't have money anymore. But anyway, this is pretty sophisticated. It finds its own ways, but also detects obstacles and including human, and can go around them. Let's talk a little bit about manipulative robotics. How am I doing with time?
You still have.
Great. So we talked about self-driving. Let's talk about self-doing a little bit. I've been working in that space a little bit as well, and we're making more progresses. You saw my latest robot, can find its own ways, can detect human, can go around them. If needed, they can stop. So there is still a lot of room for improvement in that space. Like my robot and any robot out there, they will stop in front of tall grasses. If we're a human driver, I would just push through relatively tall grasses, right? But these robots just find them to be obstacles and they stop there. If there is a hanging branch, little flimsy, you could push through, but it will stop. Versus sometimes this branch could be pretty sturdy, 3-year-old branch, so you don't want to push through. So these robots don't have that kind of capability, for example. And even in the guidance, row following is perfect, turning, a lot of room for improvement. When it comes to actually open field, like from loading station to the entry of the 3 rows, you could take any possible routes, and that's still area for. So anyway, a lot of things we could do. But there has been a lot of progress in that space. But in manipulative robotics, we are still quite far behind. There are a lot of efforts in this area around the world. These are just some example research programs that are working on fruit harvesting, such as apple picking, vegetable picking. By no means this is an exclusive list, but just wanted to give a sense of the broad breadth and depth of the research programs around the world in this space. That's certainly also because this is a challenging area that we have not been able to break through to get to the commercial adoption. In addition to public university-based research programs, there are also a lot of private companies putting their efforts in developing robotic harvesting solutions, such as this company from New Zealand, Robotics Plus. They're focusing a whole lot on Q and apple harvesting, but as I also know that recently they have been coming up with alternative robotic solutions for spraying and fruit handling in packing houses, where they found ways into getting those products into market as commercial products And I think they're still working a little bit in fruit picking, but again, in terms of commercialization, they're not there yet. Similarly, Harvest Crew down from Florida, they have been putting a lot of efforts into strawberry harvesting. Not quite commercially available yet, but I think they're making a lot of progresses. FF Robotics out of Israel. This is the company I have been working really closely with in the last 7 years or so. I often forget how many years we spent after pandemic, but this was before pandemic, so it must be 7 years or so. They're putting a lot of efforts in apple picking, really laser focused on that. Advanced Fans was a company recently went out of business actually, and that also indicates how challenging this space is. They're making a lot of progresses. They're one of the best companies in terms of the performance of their machines in real world orchards. But about a year ago, I believe they announced bankruptcy and moved on to something else. Tevel is a company out of Israel. It's very interesting, slightly different in terms of technology because they're using flying robots like these to pick apples. And if you do apple picking robot as Google or LinkedIn or YouTube, I think this will pop up first because it's been almost, it looks like a sci-fi. Well, everything is sci-fi because that's not reality yet. But this is like 10 of these flying robots right next to each other, picking apples and dropping onto a container. It looks really interesting video if you haven't watched that one. But hopefully after watching that, you can watch my video as well. In addition to robotic picking of fruits, we've been putting a lot of efforts around the world in automating other farming operations such as pollination, pruning, thinning of different kinds. Again, mostly the stuff I'm presenting here is related to specialty crops. And if you go beyond that, there are many other companies and universities working in other areas as well. I want to also point out the efforts from Harvard University. And actually, that started at Stanford or UC Berkeley. And that professor moved to Harvard, and they worked on creating flying bees for 20 years or something like that. The eventual goal was to have those bees act like bees and do pollination in addition to many other things. They have their own challenges. The really tiny robots and power and endurance have been really challenging. But then more conventional robotics, like using arms and hands, we're doing a lot of kind of conventional robotics in pollination and pruning and thinning and other aspects of farming. In this mix, my research program in the last 15 years has been putting a lot of efforts as well, trying to improve some of the limitations of these machines in speed, accuracy, robustness, and cost. Much of the work that I'm presenting was conducted at Washington State University. That's where I spent 15 years until about 5 months ago. Before getting into the machines that I work on and robots that I work on, I wanted to briefly summarize the kind of the more fundamental kind of pieces that go with the robots and help them be more robust and reliable. In my research program, early on, I spent a lot of time understanding human-machine-plant interactions. And if it is animal agriculture, maybe you could add animal interaction. But my focus has been to, for example, understanding how human pickers pick apples. What is the motion involved? What are the forces involved in each fingers? And utilize that information to design robotic hands that could be as simple, but also be able to effectively pick fruit. Been also working a lot in optimizing machine vision systems or computer vision systems for outdoor applications in orchards and vineyards. Early on, when deep learning was not there, and many of you perhaps worked with deep learning models one way or the other, including ChatGPT, for example, There are a group of deep learning models based on what we call convolutional neural networks. Those are used in image processing, and that is the fundamental of everything we do in robotics for agriculture. Before those advancements, machine vision was a real challenging problem and a huge bottleneck. And we were using artificial lighting. We were creating tunnel-like structure in orchards and using artificial lights to create uniform lighting so that sunlight would not bother. We're working a lot in nighttime. That's when it is better, more uniform with artificial lighting. But then with deep learning, we're much better. We don't have to have a kind of tunnel around trees anymore, but we still sometimes use artificial lights to and very fast shutter speed to minimize interference from external lighting. We also do a lot of optimization of AI models for agricultural applications. In recent years, I already mentioned about it, but we're looking into developing AI models for differentiating hard versus soft obstacles in farming, whether that be for self-doing, like robotic picking. I need to know if it is leaves, I can push through. If it is branch or trellis wire, I need to avoid. Same thing in the ground. If it is grass, I can push through. If it is a rock, I have to stop. Also interesting, if it is really rainy season and there is a lot of puddling or muddy surface, do I go or do I stop? I mean, those kinds of challenging questions that I'm trying to answer. Generative AI, like ChatGPT kind of models to help with vision systems. I also work a lot in innovating manipulators and in effectors or hands. Different kinds of hands, cutting, pollinating, picking, different kinds of manipulators, simpler, low-cost manipulators, so that, again, we can make the overall robotic system cheaper. So let's look at some of the videos of the prototypes that I have developed using some of those fundamental work plus system integration into a complete system that goes into the field and does what it is supposed to be doing, except it's not quite there yet. In the next couple of minutes, I would not be really talking. I was saying, Dan, earlier that I work in physical systems, which kind of speak by themselves, so I don't have to explain a whole lot. Versus there are a lot of seminars where I have to be really engaged.
I'm wondering, is the bin right under, or there's no bin there?
Very good question. I'll come to that in a little bit. Now you see.
Catch it now.
Does it sense any fruit that's already bruised or has pests or disease?
Good question.
Already?
Yeah, good question. So I'll come to all of those questions now. So first of all, I was so happy just to detach them, and I didn't care where it would go after that. That was my first prototype, 2014, 2015. Just was young professor. I got USDA funding first time in my life for robotic picking. Nobody was doing robotic picking in the US for apples. I was almost like feeling like I'm the one. But that proves to be like really challenging, and I'm nowhere now. But then just detaching was a big deal initially, so I was just dropping on the ground. And then I added another catching robot that is synchronized with the picking robot, and that would take to the container or a conveyor belt. And there was a third robot, if you noticed, who was removing that fruit from the catching robot. Looks like you didn't get my joke. But in terms of quality parameters, these cameras are really good in terms of see what they can see. They can kind of, let's say, determine the color, shape, size. Certainly, only in the part it is visible to the camera. And any defects there, it can also detect that. There are some sensors can also do some reasonable estimation of sugar content, what you call bricks and firmness. But not a lot of these robots are utilizing those technologies yet. Any other questions?
Do the robots only work on 2D trellis systems?
Good question. Even so, I mentioned earlier, best of the orchards in the world that I have seen, best of the robots we have developed in the world that I have seen, they still pick about 65, 70%. So there is a lot of room for improvement, even for the modern 2D fruiting wall orchards. Particularly, Washington State is interested in bee, and I have a lot of reservation what I can do there. But New York is better because it looks like most of the orchards here tend to be vertical or go vertical. How are we doing in terms of time? About 10 minutes left. So give me like 2 minutes, 3 minutes to wrap up, and then we'll go to questions and answers. Is that okay? So as I mentioned earlier, I have been integrating robotic system for a lot of things in orchards. Flower thinning. This is an easier audience because I don't have to explain why we need to do flower thinning, I hope. And then pollination. Now, maybe I need to do a little bit of explanation here because in the East, natural pollinators may be enough to pollinate our crops. In Pacific Northwest, we don't have natural pollinators. We hire, or they hire, a lot of beehives. And so robotic pollination becomes an important factor. More interestingly, with robotic pollination, I believe we can revolutionize farming with robotic pollination because I can place fruit where I want, uniformly separated from each other in all parts of the trees. But then it is also accessible for my robotic picking machine. Now I can pick 100% of the fruit if I'm placing them correctly. A lot of work on robotic thinning for fruitlets, and then some as a summary, some numbers here. Better, some aspects are better than other. Speed also included. There are research papers if you need to know more about that. I don't think I want to talk about that anymore. So when we integrate manipulative robotics and navigational robotics, then it becomes an autonomous system for farming. There have been a lot of efforts in this area for from private companies as well. I just wanted to show this video. This is my autonomous system for nitrogen application at individual tree level. It does sensing, decision support, and applies what it needs to apply to root zones using various kinds of sensing and image processing and decision support models. We've been doing similar work in strawberries as well. And then final thoughts. I think I ought to stop here. We're making a lot of progresses, but there is still a lot of room for advancements and eventually potentially getting it to farmers' hands. Total autonomy, in my opinion, is needed because if I automate picking, but I don't know how to send that fruit to a container bin, I would not be utilizing the machine. If I know how to pick, but this machine, if it doesn't find its way into orchards, then I'm not done. So total autonomy. There are a lot of questions around it. I mentioned most of this already. I just want to emphasize that with robotics, I think agriculture is as cool and sexy as computer science or electrical engineering or space technologies. And hopefully we can attract new generation to contribute to this area, which hasn't been as attractive in the past, in my opinion. I'll take this opportunity to thank you, Dr. Kumar, and everybody else for inviting and giving me this opportunity. And I have maybe 5-7 minutes for any questions and answers. Oh, sorry.
I very much enjoyed that. Thank you. I was wondering, with some of the technology, like certainly the earlier technologies, was sort of hybrid in that you're not looking for completely autonomous, but that may be more human assisted. Actually, the auto steer in tractors there's still somebody sitting in the tractor, and just to make sure that things don't go wrong, or just steering it the right way. And I can imagine that some kind of a hybrid system where you still use humans and take advantage of what humans do really well, like, for example, identifying 100% of ripe apples that need to be picked. but assisting them in some way.
Yeah.
With some kind of a robotic system, whether it's either, something that moves with them or maybe a robotic arm or something like. Is anybody doing kind of work in that area? Because it seems like it's a really heavy lift to go from human only to autonomous only.
Yeah.
Right?
Thanks. Very good question. The question in brief is that the systems we saw here are going mostly towards fully autonomous, fully automated way of farming. Can there be a hybrid system? Are there people working in hybrid systems that would assist human workers for improving their safety, maybe improving their productivity, and reducing overall labor use? And the short answer is yes, there are people working in that area. For example, self-steered platforms where workers get onto pick fruits and they don't have to use ladders. They don't have to go down to empty their baskets or bags. That improves productivity. I have seen numbers around 15–20%. There are people who are also investigating technologies like Google goggles that would help them, like which fruit is ready, which branch to be pruned. Those kinds of efforts are there. In my research program, I don't do that kind of work that much, but I would like to add that I'm interested in and started working on virtual reality-based interaction between human workers and robots. Robots would still be operating in the field. Workers would be in a room like this, and they would assist robots and do better job if they are failing in certain situations. So I'm interested in working, or started working in that space for human-robot interaction. But there are other people, other programs working in the area that you mentioned. So before I come to you, I think I'll give you an opportunity. You raised your hand earlier. Do you have that question?
It's about the apple picking, because you mentioned that one of the limitations is speed, right? Speed is one of the limitations. And I've seen some companies advertising some robots, especially in field crops, that can work overnight. So robots can work long hours. So how companies and universities are tackling specifically this speed?
Thank you. The question was, I mentioned speed is a limiting factor. But then the question here is that, or rather comment is that, but then they can work 24/7. Not quite that, but they can certainly work much longer hours than human. And I'll often use the number like 20 hours a day, 6 days a week, with some downtime or maintenance time. But then that is at least twice or sometimes 3 times more than a human worker. So that's certainly a benefit or a strategy that we could utilize. Eventually, it comes down to economics. Is it given the cost and the speed and the working hours? And I didn't mention that earlier, but I can add 12 amps. I don't have to have only 1 amp in my robot. But then all that increases cost. Does that eventually make the economic viability for growers is the question. We're trying to answer that many different ways. The trajectory certainly is that the manual labor cost will go up, and hopefully technology cost would go down. At some point, we'll hit that sweet spot fairly soon. We're not quite there yet.
Are there any limitations with how orchards are currently designed to need to be accessible for people, that if you were to make changes to that, you can make robots more efficient in picking or weeding and things like that?
Great question. Thank you. The question is it how, I think to simplify it, what is the impact of orchard or crop planting systems or designs? In robotics, I think it's as important as anything else, maybe more important than anything else. We have seen that no matter how much effort we put from engineering side, there is a roadblock we're hitting. About 65% picking, for example. All these companies and my research program have shown that, and other research programs have shown that even in the best orchards, I mentioned this earlier, just repeating, even in the best orchards, we're picking only about 65%. Is that enough? Maybe, because you could use this human robot collaboration. Robot would pick 65%. They would have a smaller crew of human workers follow after that, and maybe you're still benefiting from it as long as it makes economic sense. But then any way we can improve orchard designs for apples or any other crops, if we improve crop design, crop architecture such that more fruit are visible and accessible to robot, it will help the overall performance. Go.
So this might be a naive question. So compared to the Tesla and Waymo and all those self-driving platforms, how are the navigational aspects here different from those? And is it a problem of better sensors or better software or better hardware?
Thanks a lot. Very good question. A question is around how orchard navigation or agricultural navigation is different than, or similar to and different than self-driving cars or self-driving technologies that Tesla and other companies are working on. I think the larger difference, in my opinion, is investment. They have invested billions, maybe, I don't know, trillions, if that is also possible if you combine everything that's going on there. They have collected billions of images, all leveled, of everything that happens in the roads, and that creates certainly much more powerful models. We are just putting a few 100,000 into collecting a few thousand images and trying to take it baby steps. Because the model developed for road conditions does not translate into farming conditions, because we're looking into completely different environment. If we don't talk about developing countries like Nepal, where they have 3 lanes of cars in 2-lane road, mostly driving is structured. You have signs and symbols and rules, and that makes it much more structured for self-driving cars. But still, you have billions of images, thousands of different situations that you need to take care. Agriculture is even worse in terms of variability, but we don't have as much investment going into that.
All right, we are at time. Let's thank Manoj one more time.
Thank you.
This has been a production of Cornell University, on the web at cornell.edu.